This video is going to be mostly about how to calculate empirical formulas and molecular formulas, but the first thing I want to do is explain how that data is actually collected. And this will just be a nice brief explanation. So the first experiment is something called elemental analysis. So what happens is you have a sample with carbon, hydrogen, nitrogen, and or oxygen. You load it into the machine and it's burned like crazy. And you burn it so that you make carbon dioxide, water, and some NOx gases, nitrogen oxides. Everything's being oxidized. All right, it goes through and then a scrubbing process begins. Scrubbing means the absorption of various materials, and you have selective scrubbers, and by scrubbing the carbon dioxide, you can calculate the mass percent of carbon that came from the original material. Same thing can be said for water to calculate the hydrogen percent. And then nitrogen, it goes through a reduction process. I believe it makes nitrogen gas. That's counted, and you get a mass percent of nitrogen. For the oxygen that was in the original material, we get that from subtraction. So if I had like 10% carbon, 20% hydrogen, 30% nitrogen, I would say all the material, including the oxygen, adds up to 100%. I just subtracted 10 to 20 to 30 from the carbon, hydrogen, and nitrogen, and I would get like 40% oxygen. I'll show you an example of that in a bit. But long story short, elemental analysis gives us mass percent data. All right, the second experiment we're going to need is mass spectrometry. All right, inside a machine, you're going to put in a sample. It's going to get sprayed into a mist. All right, and we're going to whack it with electrons, and the electrons will knock off other electrons on our molecules, and we'll be left with ions. In this example, I drew them as positive ions. All right, you accelerate through an electric field, and there's a magnet nearby, and charges interact with magnets. So there'll be some a little bit amount of attraction towards the magnet. You don't want it so strong a magnet that you're going to bump into the magnet instead of the detector. But hopefully we don't need to get into too complicated of physics here. Basically, the heavier things, they're just going to have more inertia. So the heavier molecules or molecular fragments won't get deflected as much by the magnet, whereas the lighter ones, they'll get more deflected. And based off of how long it takes to hit the detector, the lighter ones will take longer to hit the detector. Where it hits the detector, all these sorts of possible sorting mechanisms. The computer will just use math to calculate based off of the charge on the ions, acceleration, electric field, velocity, magnetic field strength, blah, blah, blah. You calculate the mass of the molecule. And that can be done actually to a high enough precision and accuracy. You can actually even tell different isotopes apart. Pretty cool. Do you need to know these experimental techniques to do these problems? No, but I just thought that'd be kind of interesting. So the long story short, we get empirical formula data from mass percent data, and we're going to get molecular formulas from the molecular molar mass data from the mass spec. So elemental analysis and mass spec. All right. So here are the 6 steps we're going to follow to do these example calculations. We have 2 examples for today. All right. And this may not make sense until we actually do the problems, but I just want to say it on record. So first, we're going to take our mass percents. We're going to convert them to grams. Then we'll take our grams and convert them to moles. From our moles, we will get mole ratios. And these mole ratios, we will see that it's actually our empirical formula. After that, we're going to, let me pause right here. If all the problem's asking for is an empirical formula, we are actually done. But if they ask also for a molecular formula, or that's all they're asking for, then we have to do these extra steps here. We're going to calculate the molar mass of the empirical formula. I like to abbreviate that EMM, empirical molar mass, M. All right, I'm going to have a bunch of silly acronyms and sounds here. We're going to calculate something called a subscript multiplier. We're going to take our molecular molar mass. I'm going to nickname that and we're going to divide that by M. So yumminess divided by hesitancy. All right, and then step number 6 is we're going to find the subscripts in our empirical formula, multiply them by our subscript multiplier, and then that will be our molecular formula. All right, 6 steps. I really prefer this method of calculating because, well, let me put it this way. Some other methods exist out there on the internet and such, and people will calculate the molecular formula first and then work backwards to the empirical formula. That technique does not always work if you were not given the what's it called? The molecular molar mass. So if you're wondering what I'm talking about, you're really curious, feel free to message me. But otherwise, I think most people will be better off not knowing about that other technique that exists out there. All right, let's cut to the chase and do some example problems. All right, example number 1. Find the empirical formula and the molecular formula based off of this mass percent data and this molecular molar mass. All right, it's a compound that has carbon, hydrogen, and oxygen in it. So it only has those 3 elements, but they didn't give us the oxygen, which means we will have to go out of our way to calculate that. All right, so let's do it. So everything should add up to 100%, right? So that means to get the percent oxygen, we will do 100 minus 39.99 minus 6.73. Okay. I'm kind of out of space there, so I'll calculate it here. If you're wondering about the sig figs, this 100% is considered an exact number, so you can give it as many sig figs as needed. All right, so 100, make sure there's no glare, minus 39.99 minus 6.73. Boom. All right, 53.28. Percent. All right, so step 1 is done. You know what? Let's just do this on separate paper. That's gonna be better. Actually, what am I talking about? Step 1 isn't done yet. We haven't even started yet. This was like step 0 to figure out what the percents were. All right, so let's just rewrite those datums. No, data's plural. And I've heard from some viewers that some people like to play my videos at like 1.5 or 2% speed, and that's totally fine. I am not offended at all. I take it as a compliment if I'm a slow talker. I like to talk slow, try to make sure people understand me. All right, so we got our percents. Now we're going to do the step of converting our percents to grams. So in the mass percent data, they don't usually tell us how much actual material they use to do the experiment. And actually, that's not very important. In fact, I think it's easier to just pretend to assume that you had 100 grams of material. So 39.99% of 100 grams, let's say we have 100 grams exactly. Well, guess what? That's going to be exactly 39.99 grams. So assuming you have 100 grams makes your math way, way, way easier. You just change out the percent symbol for a gram symbol. 53.28 grams of oxygen. if you want the exact formal step of converting it, I guess I should have maybe written 39.99%. To convert out of percent, you have to divide by 100%. And then we multiply by 100 grams. That's what I was doing over here. I know for my students, I just tell them it's totally okay. Like if we had this on an exam and I wanted them to show their work, I'm okay with them just saying step 1 like that. They don't even have to label their steps if they don't want to. They just write these values with grams instead of percents. All right. All right, so that was step 1, actually step 1. All right, so step 2, we're going to change grams into moles. And to do that, we will need a periodic table. So we're going to need the molar masses for the elements involved. We have carbon at 12.011, hydrogen at 1.008, and then oxygen at 15.999. All right, so let's get the moles. Let's see, 39.99 grams of carbon. And we'll do some dimensional analysis. We need grams of carbon at the bottom and moles of carbon at the top. So using a molar mass from the periodic table, periodic tables, we read this as 12.011 grams per 1 mole. So that means the 12.011 goes with the grams, and the 1 goes therefore at the top. All right, let's do this for the other elements. Notice I like to set up my math before I even actually calculate anything. Just clearing some desk clutter. Let's see, 15.999 grams. And those who haven't seen my previous videos, I like to write oxy instead of O, because O looks to me too easily like a 0. All right, those units will cancel, leaving us with moles. All right, 3.329 for sig figs. Moles carbon. 6.73 divided by 1.008. 6.68. For correct sig figs, just 3 there. All right, and then lastly, we have the oxygen. And don't just, well, I mean, I suppose you could just simply watch this and that's fine. But if you're not really understanding, I recommend to most everybody that you try the math, write down the work yourself to really learn and get that memory and experience. All right, so here's my numbers. All right, if you are not getting the same things as me, pause and revisit your work. Make sure you didn't have any calculator error or anything like that. But here's our mole amounts. These amounts don't fully mean anything yet, but we're on to something. Okay, so to kind of recap what we've done so far, we got the grams, and we can't like compare the grams directly to each other yet because, well, carbon has a greater mass than hydrogen, and oxygen has an even greater mass than carbon. So you can't really compare the numbers of atoms for masses. Whereas moles is more powerful because the unit of moles is comparing, it's a count of how many atoms I have for that element. All All right, it's proportional to that. So here is more of a apples to apples sort of comparison. I hope I'm using that idiom correctly. Even before we do step 3 with the mole ratios, perhaps you can anticipate some math coming. I know that's maybe not a strength for everyone, but for me, like, I can kind of see these are about the same number. So that element and that element will be probably a 1-to-1 ratio between the carbons and oxygens. This moles of hydrogen, 6.68, this to me looks to be about double that of the carbon and of the oxygen. So maybe we're looking at a 1 to 2-to-1 ratio between these elements, but we're going to calculate those mole ratios just to be on the safe side. All right, so let's keep going. Ooh, I am running out of paper. All right. Okay, here we go. So step 3, we will turn our moles into mole ratios. All right, so what you need to do here is revisit your previous calculations. And in order to get mole ratios that are easy to understand, it is easiest for you to find the smallest number. So I'm going to circle this moles of carbon as my smallest number. All right, we're going to use the smallest number because it's going to give us numbers that are 1 or greater, which is easier for us to understand. You'll see hopefully what I mean in a moment. All right, so here is how we do the work of mole ratios. So to get the number of carbon atoms, what we'll do is we're going to take the moles of carbon and then we're going to divide it by the lowest number of moles. Similar process for hydrogen. Moles of hydrogen over the lowest number of moles. Same thing for oxygen. To be crystal clear, that our denominator, the bottom part of the fraction, will be the same value each time. I circled it in red, and I'll circle it here as well. All right, so let's plug in the numbers. The moles of carbon is 3.329. And since carbon provided us the lowest number, we'll just write it again. I'll just use red to emphasize we're using that same one every time. All right, so that's setting up my first calculation. Our moles of hydrogen, 6.68. Divide by 3.329 moles again. And then we got 3.3, what was it? 3.330 moles of oxygen. And again, we're going to divide by that lowest number, 3.329 moles. Okay. Our moles cancel, leaving us with just the units of the elements themselves. Let's calculate these numbers. So, well, this one we can do in our head. I'm feeling silly. Let's just do it on the calculator. 1 carbon. Okay, if you want sig figs, 1.000. Anyways, but it's 1 carbon, y'all. And then 6.68 divided by 3.329 and 2.01 hydrogens. And at this point, we're just going to declare that to be 2 hydrogens. All right, experimental data is not always going to be super duper perfect and spot on. So if you're like just like 0.01 off or 0.02 off, you can typically be pretty confident in that number. I know when I find data make problems for my students, then I usually give them an assurance that you're not going to be more than 0.01 or 0.02 off from a whole number. All right, and then the oxygen, 3.330 divided by 3.329. This will basically be 1. Yeah. 1.000 oxy, which we'll just declare to be 1 oxy. So what does this mean? This means we have an empirical formula. All right, so I'll put this in a red box. I'll put this one in a green circle, and I'll put this last one in a blue fluffy cloud. Happy little cloud, Bob Ross style. And we have an empirical formula of C1 2H or H2 and O1. Okay, that is our empirical formula. All right, C1H2O1. Well, of course, in chemistry, we don't write the ones for subscripts. So the actual way to write this would be CH2O. Okay, fine. There's the real final answer for the empirical formula. So again, if this is all the problem was asking for, an empirical formula, you're done. But the problem asked us to also get a molecular formula. So we are only halfway through this problem. But this wasn't wasted time. We actually need this empirical formula to continue the problem. So let's continue. Step 4. Step 4 is to calculate the empirical molar mass. We want to calculate the molar mass of the empirical formula. So our empirical formula was CH2O. In this formula, we have 1 carbon, we have 2 hydrogens, and we have 1 oxygen. So that's going to be 1 times time to get the periodic table. Actually, we looked these up earlier, didn't we? Well, here it is again. 12.011, 1.008, 15.999. All right, everything is in grams per mole. So our carbon subtotal is 12.011. Our hydrogen total is 2.016. And our oxygen total 15.999. Okay, so the sum of all this will be our empirical formula's molar mass, EMM. And let's do it. All right, so 12.011 plus 2.016 plus 15.999. 30.026 grams per mole. All right, I think we can do everything still on the same page. Step 5, we are going to calculate what I call the subscript multiplier. The subscript multiplier is our molecule's molar mass divided by our empirical molar mass, M. The molecule's molar mass, it might feel like ages ago already, but that was provided at the beginning of the problem. Okay. So remember, mass percent data is for empirical formulas. The molecular molar mass is for molecular formulas. And they gave us 180.2 grams per mole. This is common in many chemistry problems that they'll give you like a molar mass for the molecule that isn't like super duper precise. I mean, this is like decent. It's in the 10th place, but often they'll like even put into ones place. I will say in reality, that's kind of a disrespect to mass spectrometers. They can often get a lot more precise data going, even the medium range ones will probably be able to give you like 3 or 4 decimal places out. And then the very high end ones for like publishing periodic table data, they can go even more than that. Anywho, that's a side tangent. So 180.2 grams per mole. And then we'll divide it by the 30.026 grams per mole. Goodbye go our units. So basically the idea of the subscript multiplier, as I try to find my calculator, is to see how many times this empirical formula fragment fits into the actual molecule. This feels like it's going to be about 6 to me. But we need to confirm, and yeah, that's 6.001. And at that point, we can be like, okay, that's pretty darn good. That is a 6. All right, so let's take out our empirical formula again. We had C1H2O1. And now this multiplier of 6, I'll put it in, I already have it in that green circle, so I don't need to bust out this orange. I like to use colors. I was looking for an excuse. So there it is right there, multiplying by 6. We'll multiply by 6 again. Use that subscript multiplier for all of the subscripts. So 1 times 6, we will get C6. 2 times 6, we will get 12 hydrogens. 1 times 6, we will get 6 oxygens. And here is our molecular formula. All right, that fit pretty cleanly, so I'm like pretty confident in that answer. But if you wanted to, and we had done step 6 here. This was step 6. I guess these are kind of combined into a step, whatever. But if you wanted to check your work, especially if it's like a high leverage situation, you're like publishing research or something, then you would probably want to double check this. So we can do a quick double check. It does not take too long. You don't even have to be exact with your math if you don't really want to be. Yeah, I'll prove it. So here's our double check. If our molecular formula is truly C6H12O6, we should be able to use this formula with the periodic table, and we should get a molar mass pretty close to the 180 grams per mole. Whatever they gave us earlier. What was it? 180.2. There we go. Grams per mole. So let's do that. 6 carbons, 12 hydrogens, 6 oxygens. And again, you can use the exact numbers, but just for a quick ballpark check, we can just, I'm just going to call carbon a 12. I'm going to call hydrogen a 1. I'm going to call oxygen a 16. Um, 12 times 1 and then 6 times 16. So it's 72, 12. What's 6 times 16? Oh my gosh. 96. All right, and then sum that up. 9. Yeah, we get 180. All right, and so, some people can do this math in their head. I don't. I normally can sometimes, but I'm pretty tired right now. But 180, it's in the ballpark. So I am pleased with this result. One more example. That example worked pretty cleanly. That's not always going to happen. So that's what I have planned with this second example. So somewhat similar looking data. We have carbon, hydrogen, and oxygen again. They were nice this time, and they provided us the oxygen percentage. And then there's the molar mass, and same question being asked. Please calculate the empirical formula and find the molecular formula as well. All right, so let's do this. Let's see, will orange work today? Yeah, that's good. Okay. So let me get some paper. Hang on. So step 1. Percents into grams. So let's just write for carbon, we will write 40.91 grams carbon, 4.59 grams hydrogen, 54.50 grams of oxygen. All right. And then for step 2, we will turn those into moles. Here, I'll box that off. Oh yeah. You caught me pausing because I realized I used a different periodic table than this one. I'm using a periodic table where there's only 2 decimal places on the numbers, but it's going to be fine anyways, no matter what periodic table you use. Sometimes it's nice to carry 2 extra digits beyond the sig figs. We'll see if that comes to bite me or not. All right, let's see how we're doing so far. All right, we got our moles of carbon, hydrogen, and oxygen. We have a tie for first place between the carbon and the oxygen. Kind of like the previous problem. I should have chose maybe something more different. Oh well. Step 3. Let's get that mole ratio. Ratios. Ratio. I think it's singular. All right, so for our number of carbons, divide by our lowest mole number. Number of hydrogens will be our moles of hydrogen. Divide by our lowest mole number of moles. All right, and our lowest mole number, it's a tie between those two. I'll just circle this top one. Sometimes I'll just really signal it to myself. Lowest number of mole. Yeah. All right. Some people will. I'm feeling a little bit silly. There used to be old internet jokes about people letting go of shift too early when they type a lot of exclamation marks. I don't see that so much anymore. Maybe that gets auto-corrected now. I don't know. All right, anywho. All right, and then let's get those numbers. I'm out of room, so I'm just gonna continue it down here. This is where I'll put my answers. Well, that's gonna be a 1. And that's going to be a 1. So we have 1 carbon, 1 oxygen. Let's do the final one, 4.54. And then we'll divide by 3.406. All right, this is not looking like a clean divide. Let's confirm. It is not. We get a 1.33 hydrogens. All right, take a deep breath. We now are in, actually, this is a somewhat common situation. This is a situation where we are going to have to think a little bit about fractions, decimals, things like that. So, let me show you how to deal with this situation. I had to get more paper. So, all right, so here's how we deal with this situation. So first off, technically speaking, mathematically speaking, this right here actually is an empirical formula. There is no rule saying that you have to represent empirical formulas as whole numbers. Except I just lied. There kind of is. In Chem 101 and maybe Chem 111, in some chemistry classes, especially like maybe like introductory ones, or it might even depend on the instructor, they are going to mandate quite often that you must put your empirical formula as whole numbers. So this ratio between 1 1⅓, and 1 will still hold, but we just have to turn that into whole numbers, okay? But yeah, mathematically speaking, I like math, me personally. You could still get the molecular formula correct from this empirical formula. But let's turn things into whole numbers. So to get whole numbers, I'm going to show 2 methods for whole numbers. 2 methods for whole numbers in empirical formulas. All right. So I'll show 2 methods. The first will be the add to yourself method. All right, or to itself. I just pretended you were that, or I was that. Anyways, whatever, you know what I mean. So you just kind of look at this and you're going to be like, okay, I'm going to see if taking that empirical formula and adding it to itself will result in any whole numbers. So let's do that addition, and we will get C2H2.6602. That's still not a whole number, so we will try it again. And basically, you just keep on doing this until you get numbers that look clean, aka whole numbers. All right, so 2 plus 1 gives us 3. 2.66 plus 1.33 will give us 3.99, and that is basically 4. That now falls into our, or at least my, plus or minus 0.02 sort of guarantee. And then 2 plus 1 is 3. So at that point, we say, that's within reasonable experimental error. So we have C3H4O3 as our empirical formula. Okay, so that's the add to yourself method. In my teaching experience, people overwhelmingly enjoy this method. But for those who have mathematical comfort, I'll call this the fraction method. And that is to realize, if we write C1, that's easy. But then for the H1.33, you realize that is the same as 4/3. 4/3, and then O1. Okay. And then you just say, oh, to get rid of this denominator, I need to multiply everything by 3. You have to do it to all numbers so that that ratio still holds. So we get C3H4O3, which is the same result. Okay, so this is that what's called an improper fraction? I can't remember. And then we can have this mixed fraction, I think it's called. 4 1/3 is the same as 1 1/3. You can think of it that way instead. But same difference, we have to multiply everything by 3 to get rid of the denominator. So that'd be a 3 plus 3/3. So that's a 4 again. And we got the same thing every time. So yeah, this is how you deal with decimals or fractions in your empirical formulas. And again, I only make my students do this in Chem 101, turn it into this, because that's pretty standard to the Chem 101 curriculum. So even though I don't like enforcing that, I have to, basically. And I think the idea that they're trying to teach and making you turn it into a whole number is getting the idea across that in reality there's no such things as decimal or fractional atoms. They want you to feel that that is nonsense. And that point is fair. That point is true. All right, we are at the halfway point for this last problem. Step 4, we will calculate the empirical molar mass. So 3 carbons. Let me rewrite what that empirical formula was. So we had 3 carbons, we had 4 hydrogens, and 3 oxygens. 3 times 12.01 grams per mole. Again, from the periodic table. I'll not be lazy with my units this time. Write those zeros, respect them. Someone measured them. Got to show sig figs when they're measured. All right. Let's do this. I could do that in my head. Come on, man. All right, and then 3 times. I can do that in my head. All right, anyway, whatever. No, I could have just done that. I'm cool with when my students just do arrows for repetitive showing work unit stuff. All right, but I do want to see those units in the final answer. That's where I care about it the most. Me personally. So 36.03 plus 4.04 plus 48.00, we get 88.07. Grams per mole. All right, step 5, let's get that subscript multiplier. That's going to be our molecular molar mass divided by our empirical molar mass. So at the beginning of the problem, 176 grams per mole. And divide that by 88.07 grams per mole. This feels like a 2. I like to make predictions in my head. And yeah, 1.998 to 3 sig figs, that's 2.00, which is just 2. All right. So I'll put that in a circle. And so earlier we had C3 times that 2, and we had that H4 from earlier, times it by 2. And then oxygen, 3 times that 2 right there. So that will be 6, that'll be 8, and that'll be 6. So C6H8. O6 is our molecular formula. Well done, everybody. By the way, if you're curious, this is the chemical formula for vitamin C. That's why I was using orange earlier. Made me think about eating oranges. And example 1 had, what do you call it? A monosaccharide, hexose sugar, like glucose or something. Simple sugar. All right, so in conclusion, this video is almost over. Yay. Conclusion? I don't know if there's really conclusion. More like a final thought. My final thoughts on empirical formulas. And this is me kind of personally speaking as a teacher. So we saw earlier that for the vitamin C problem, we had an empirical formula involving a 0.33. That's kind of a third, right? So, you know, if you have something, you know, some number and it's ending in 0.5, that should hopefully remind you of like a half. You're going to end up needing to, you know, that's about like a half, right? So, so that's going to mean you're going to end up needing to like multiply by 2 to get rid of that denominator. If you have something like 0.33, that's going to be about, you know, a third over there. Well, I guess we don't really know what's over here, but it's going to, forget this. I'm getting tired, so I'm not starting to make sense. If it's like a 0.33, get multiplied by 3. If it's like 0.66 or like 0.67, you're going to have to, you know, multiply by 3 again if you're into finding multipliers. You know, 0.4, that's like, you know, 4/10, which is the same as 2/5. So it looks like you'd have to like multiply by 5 there. So, I mean, if you want to have like a fractional approach, this is another way to think about it. But me personally, I probably like started out this way, and over time, I'll tell you what, even with, you know, someone with, you know, advanced degrees or whatever like me, I have found myself liking this add onto yourself method quite a lot. I don't have to think fractionally or anything. I don't even have to really think when I do it this way. I find it a pretty fun way to do things. So I think this video is long enough, so let's close things here. But thanks for your time and attention and energy. Any questions, comments, suggestions, let me know. But otherwise, take care.